Today I will be talking about our work on understanding the lifecycle management of data center topologies, lifecycle management complexity of data center networks. And this is a joint work from between people from University of Southern California and VMware Research. So data center networks are important facilities for cloud computing, and there is a long line of work on topology design in our community. For example, a Clos is a multi-rooted tree with layered structure. Clos can scale to arbitrary size with low radix merchant silicon switching chips, and it is widely deployed in practice. Recently, there is another family of topologies called expanders that attract people's attention. For instance, expander graph can use much smaller number of switches to achieve the same performance compared to Clos. So for example, Jellyfish is one instance of expanders, and which is a random graph with bounded node degree. Another instance of expanders is called Xpander, and the whole topology is a clique of meta nodes. And the meta nodes is a cluster of switches without links between each other. So most of previous design focused on achieving high performance at a low cost. However, designing for manageability has received very little attention. So our work considers an orthogonal dimension of topology design, that is management complexity. Specifically, we ask the following question: how does the complexity of managing data centers depend on the topology? And to answer this question, we focus on studying lifecycle management of data center topologies. Lifecycle management is a process of building a network, deploying it on the data center floor, and expanding it over several years to serve the constantly increasing set of services. Management complexity is important. A design that is hard to deploy can stall the rollout of new services for a long time. This can be expensive considering the increasing traffic demand. Also, as previous talk mentioned, topology expansion leads to capacity drop. And a design that is hard to expand will leave the network functioning with degraded capacity for a long time. To understand lifecycle management, there are several challenges to be solved. So the first challenge is how to characterize the management complexity. To solve this, we propose several metrics to quantify the lifecycle management complexity by considering practical physical constraints. The second challenge is how does topology structure affect the management complexity? By leveraging the metrics we developed, we compared several representative topology families, and we found that no topology dominates by all our metrics. And also from this study, we derived some principles on achieving low lifecycle management complexity. And at last, we are wondering if there is a topology with low management complexity, low cost, and high performance at the same time. By leveraging the principles we learned, we designed a new topology family called FatClique, which achieves all these nice properties at the same time. OK, let's look at the first challenge. So there are many dimensions in lifecycle management. For example, packaging, cable wiring, device placement, and cable rewiring during expansion. All these problems need to respect constraints from all kinds of data center devices, such as switching chips, data center racks, data center patch panels, and cable trays. We studied lifecycle management from first principles. Specifically, we understand in detail how topologies are deployed and expanded. Then we derive metrics that capture the complexity of these operations. OK, let's look at how to quantify deployment complexity. So packaging is the first step in deployment, which is about carefully arranging servers and switches into the data center rack. So since the number of switches directly determine the packaging complexity, we use it as a metric. After we packing switches and servers into data center racks, we need to connect them. And if the connected switches are within the same rack, we can use short and cheap cables to connect them. However, if the connected switches are in different racks and are far from each other in the data center floor, we need to use inter-rack links. And those links are routed over cable trays about the data center racks. And the main wiring complexity comes from those inter-rack links. Considering the scale of the data center, there are too many fibers to be handled individually, as shown in this figure. So people use cable bundling to overcome this challenge. A cable bundle is a fixed number of identical lines fibers between two clusters of network devices. And by its definition, a cable bundle is characterized by two elements. One is its capacity, the second is lines. So here the capacity means the number of fibers in a bundle. Let's look at an example. So this figure shows the top view of racks. Since the network, the topology has all-to-all connectivity, without bundling, we need to handle 16 individual fibers with 4 types of lines, which are shown in the different color in the figure. On the other hand, if we use bundling as shown in the red figure, by connecting all racks to a common aggregator, we only need to handle 8 equal lines, uniform capacity bundles, and only 1 bundle tab. We can expect that the complexity, if the number of bundle tabs increase, the complexity of manufacturing, packaging, and cable routing can increase. So we use the number of bundle tabs as one metric to quantify the varying complexity. So this figure visually shows how does bundling reduce the varying complexity of Google's data center networks. So when we talk about bundling, we have to mention one important network device, that is patch panel, which acts as an aggregator. So a patch panel is a device where fibers from different bundles are connected, and this connection is manual. Therefore, a lot of varying complexity happening at the patch panels. And therefore, we use the number of patch panels as a one metric to quantify varying complexity. To summarize, we have 3 metrics for deployment complexity. The first one is the number of switches, and then the second one is the number of patch panels. The last one is the number of bundle tabs. Next, let's look at how to quantify expansion complexity. As mentioned in previous talk, topology expansion leads to capacity drop. Therefore, to maintain a given residual capacity, topology expansion is conducted in multiple steps. So the expansion step is a natural metric to quantify expansion complexity. Next, we need to quantify a single expansion step complexity. So remember that it is hard to move existing links, which has already been routed over cable trees. So to solve this challenge, patch panels are used. Firstly, all existing bundles are connected to some patch panels. Then during expansion, we just need to connect the new links to existing patch panels. With this, we can complete the rewiring process entirely on the patch panels. But remember that the rewiring is manual. It dominates the time for each expansion step. Therefore, we use the number of rewired links per patch panel rack as a metric to quantify the single step complexity. As a summary, we end up with 3 metrics to quantify deployment complexity and 2 metrics for expansion complexity. Next, let's look at how does the topology structure affect the management complexity. We did a case study on Clos, Jellyfish, and Xpander. Here, we only show the results for Clos and the Jellyfish. Based on the results, we find that Clos performs better in terms of patch panel usage and bundling, while Jellyfish performs better in terms of switch usage and expansion complexity. So there is no topology dominates by all our metrics. By carefully analyzing the results, we derived 3 principles to achieve low management complexity. The first one is the importance of topology regularity. So Jellyfish is a topology that does not exhibit regularity. Jellyfish is a random graph, which leads to a non-uniform bundles between switch clusters as shown in the figure. Therefore, in large scale, Jellyfish has 1 order of magnitude more bundle tabs than Clos. The second principle we learned is the importance of maximizing intra-rack links. As shown in this figure, some regular part in Clos with dense links can be packed into a single rack. And those links are cheap, short, and easy to manage. However, Jellyfish does not have this nice property, so most links in Jellyfish are inter-rack links, which leads to more patch panel usage and high varying complexity. The third principle we learned is the importance of fat edge, which can significantly reduce the expansion complexity. So this figure shows a network edge, and we divide its auth links into two categories. Links connecting servers are called southbound links, and links connecting switches are called northbound links. A thin edge has equal number of northbound and southbound links, and a fat edge has more northbound links than southbound links. So let's consider a scenario that we want to maintain 75% residual capacity during expansion. And remember that since rewiring leads to capacity drop, we need to drain traffic before we do rewiring. So for thin edge, to maintain this capacity, we can at most drain 25% links at the edge, which leads to 25% capacity drop at the edge. However, for fat edge, even draining 50% links, it leads to 0 capacity drop. So from this example, we can see that more links can be potentially rewired in a single expansion step. For example, Jellyfish has fat edge, so it has fewer expansion steps, while Clos has thin edge, so it has more expansion steps. As a summary, Clos satisfies the regularity principle and maximizes intra-rack links. While Jellyfish has fat edge. So next, I will show how to leverage the principles we learned to design a new topology family called FatClique, which have achieved all nice properties. So FatClique is a topology with 3 hierarchies. In the lowest hierarchy, we build sub-block. And the design goal here is, a sub-block is a cluster of switches. And the design goal here is one or multiple sub-blocks should be packed into a single rack to maximize intra-rack links. In the second hierarchy, we build blocks, which is a clique of sub-blocks. And finally, we compose the whole network with a clique of blocks. And the design goal here is the blocks should be large enough to form uniform bundles between each other. So by construction, FatClique satisfies the regularity principle. However, maximizing intra-rack links and achieving fat edge are at odds with each other. So let's look at an example. This figure shows the sub-block in FatClique. And for each switch, it connects to 3 servers, 3 intra-rack switches, and 3 inter-rack switches. And by definition, it is a thin edge. However, to achieve fat edge like this, we need to decrease the intra-rack links per switch from 3 to 2. So from this example, we can see that achieving fat edge and maximizing intra-rack links is conflict with each other. For similar reason, achieving fat edge is conflict with minimizing switch usage. The problem is even more challenging considering other constraints in topology design. For example, we just want to provide right enough capacity. Also, we want to minimize rack fragmentation, and we want to minimize overall cable lines, and so on. Our solution is a constraint-based search. And the whole design space can be described by 5 variables. And with those variables, we can transform our principles and insights to mathematical constraints. For example, to enforce a fat edge at the switch, we want the number of northbound links should be larger than the number of southbound links. And this can be represented by this formula. After we have all these constraints, we can use it to search a topology with a given capacity and optimal manageability objectives. So to evaluate the performance of the FatClique search found by the first search algorithm, we ask a few questions. And in this talk, I will go through 2 of them, and you can find others in the paper if you are interested. So first, we ask, does FatClique have lower deployment complexity? And the second is, does FatClique have lower expansion complexity? For fair comparison, before we compare them, we always equalize the capacity of those topologies. And we compare the performance of those topologies at a different scale. And in this talk, I will only show the results at large scale. Also, for fair comparison, we designed highly optimized placement algorithm, topology expansion algorithm, and the topology search algorithm for each topology family. To show that FatClique has low deployment complexity, we evaluate different topology families in large scale. And each bar corresponds to a topology family, and the different figures correspond to different complexity metric. And from those figures, we can see FatClique performs best by all deployment complexity metric. And it confirms that FatClique achieves low management complexity since it maximizes the intra-rack links and it is regular. Next, to show that FatClique has low expansion complexity, we compare expansion steps and the various residual capacity requirement. And the x-axis is a residual capacity requirement, and the y-axis is a number of expansion steps. So from this figure, we can see that FatClique is as good as expanders. It only uses 3 or 4 steps to expand the whole topology, even when the residual capacity requirement is very tight. On the contrary, for Clos, when the capacity requirement is high, it uses more than 20 steps to expand the whole topology. This has implication for network availability. That is, to maintain the same expansion steps, FatClique and expanders can enable much higher network availability. So in conclusion, management complexity is an important dimension for topology design. And our work is the first step in this direction. And we designed several metrics to quantify the management complexity. And also, we use the principles we learned to design a new topology family, which is a better design space than some of previous designs. And we hope to study some other aspect of management aspect of topology design. For example, control plane complexity and the network debuggability and the practical routing for FatClique. That concludes my talk. I'm happy to take questions.
Just go. Hi, Nodir from UBC again. So the spoiler, we talked about this yesterday on a preview session. So just wanted to ask about performance, latency in particular. So are you modeling latency? Are you assuming you have the same latency as Jellyfish, for example?
I see. That's a good question. So for latency is maybe is a hard metric to quantify. The reason is so the theoretical metric to quantify latency is a network diameter, and the diameter for FatClique and the expander it has a smaller diameter. But those paths for those topology they do not have many of these shortest paths. So that's why. So in this topology you have to use other paths with other lines. And since we haven't considered practical routing in our design, we cannot make a conclusion about the latency. And for throughput part, we didn't use throughput. Instead of that, we use capacity. And the network capacity is a worst case, is a bound for throughput. So we are actually compare topology for worst case.
Okay, thanks.
Hi, this is great work. Congratulations. So one question with regards to performance. So I haven't looked at this very closely, but your results on the spectral gap are about 15% lower than Jellyfish, right? So at the largest scale, this is just eyeing out from your appendices. So how does spectral gap translate to throughput? Is it a linear relationship? Or so does it mean it has 15% lower throughput as well with the same switches? Or how does this work exactly?
You mean the translation between throughput and what?
Spectral gap, right? So in one of your appendices,
spectral gap, yeah. Right? Okay, so we have some results for spectral gap. To give the audience a background, spectral gap is a theoretical metric that which means if a topology has a higher spectral gap, a larger spectral gap, it might have larger capacity, right? So we compute the spectral capacity, and since FatClique has more regularity, so it sacrifices some spectral gap. But we didn't observe obvious trade-off between spectral gap and the metric we consider. And for the performance part, we didn't do experiment on real throughput, so we will leave it for future work.
So are any of your topologies available, or can you make them available? Is the code online?
Yeah, sure. We plan to make clean the code and make it public.
All right, sounds great. Thanks.
Thank you.
Dmitry Afanasyev, Yandex. Thanks for an interesting talk. I have a bunch of questions, actually. You had a slide with comparison of deployment complexity.
Can you speak
what was
louder?
On the slide with comparison of deployment complexity? What was the assumed radix of the switches?
What is what?
Radix, how many ports? Because at some point, usually you want to maximize radix. Okay. Because it decreases the number of levels in hierarchy. But this is conflicting Go with the dense packing, because after some radix, you cannot pack everything in single rack.
Sure.
So what was the radix for that slide where you compared deployment complexity?
Sure. So the radix we use is 32. And the reason we use it because we find it is the most common switch radix at different when each port has different capacity. Okay. So we find this is most common one, so we just use that.
Yeah, and another question is, do you need non-shortest path routing to?
Yes.
Yeah. Okay.
Yes.
Thanks.
Thank you.
Hey, so one more minor comment for the future. I think what would be really nice. I already like this, the quantification of complexity. What would be really nice is if we could translate this directly to cost, right? So then we would just have cost and performance. So then you could either normalize performance and measure cost, or normalize cost and measure performance. So it would be really nice to say that, for example, a human operator takes X amount of time to rewire this number of cables and put that really into cost. I know this is probably very hard, but have you considered talking to folks at Google and other places and seeing if this is, at least you can get some ballpark numbers? That would be very, very cool then.
Cool. Thank you so much.
Sure.
Okay, thank you. Another round of applause, please. Thank you.